In this course, you will learn a basic electronics understanding with little or no prior knowledge of electronics. We'll cover the history, the theory, different electronic components, and their practical application, and reinforce these lessons with demos of real-world electronic circuits. The student can follow along with a minimum of electronic parts and instrumentation and learn hands-on. Towards the end of the course, we'll cover prototyping and circuit building techniques in more detail to give you a start into creating useful circuits. So let's get started. Electricity. We see it everywhere in nature. One of the most spectacular displays of electricity is lightning, and a more subtle display is demonstrated by our nervous system in our bodies, transferring information by electricity. Electricity has been around since the beginning of time. Shocks from electric fish have been documented as early as 2150 BC. Thales of Miletus recorded observations on static electricity around 600 BC. The formal study of electricity, however, is a fairly recent pursuit for mankind, and the understanding and application of electricity has skyrocketed in a short period of time. We are still learning even today new and innovative ways to apply this mysterious phenomenon. In starting a course of study in electricity and electronics, it is sometimes difficult to know where to start. A good starting point is to take a moment to look back at the work of others, to see and appreciate how we all arrived at where we are today, and at the same time, we'll learn some useful terminology which we'll use throughout the course. Benjamin Franklin is often referred to as the father of electricity. Back in 1752, he observed electricity in clouds by flying a kite in a rainstorm, hypothesizing that lightning was electrical. A metal key around the bottom of a wet kite string jumped sparks to the back of his hand. So very little was known about electricity at the time, and certainly the potential lethal consequences of an experiment like this were not well understood. Fortunately for Franklin, he was well insulated and not in the conducting path. Others trying similar experiments were not so fortunate and suffered death by electrocution. Besides discovering that electricity existed in clouds, Franklin also observed that electricity had charge. He was the first to identify positive and negative charges. Since the time of Ben Franklin's famous kite experiment, there have been many milestones in the understanding of electricity and its behavior and effects. Much of what we take for granted today was discovered by many bright and smart scientists. Around 1780, Luigi Galvani observed the leg of a dead frog jump when a scalpel touched a nerve on the frog's leg. Galvani observed that electricity caused the frog's leg to jump, but incorrectly concluded that electricity came from the frog's leg. In 1800, Alessandro Volta had been studying the effects of how two dissimilar metals together with an electrolyte generated electricity. Because there were dissimilar metals in Galvani's experiment, one being the scalpel, and the frog's leg itself acted as the electrolyte, Volta postulated that Galvani had inadvertently generated the electricity he observed, and it did not come from the frog's leg at all. Alessandro Volta is credited with inventing the voltaic pile, which is what we commonly know today as a battery. Volta has the honor of having the unit of measurement for electrical potential, the volt, named after him. In the 1820s, André-Marie Ampère was instrumental in the study of magnetism and electromagnetics. His research was foundational in the development of motors and generators. The unit of measurement for electric current, the amp, was named after him. In 1827, German physicist George Ohm gave us the mathematical relationship between voltage, current, and resistance. The mathematical formulae are named after him as Ohm's law. The unit of measurement for electrical resistance also takes his name as the ohm. We will study these equations in detail later. The triangle with the V, I, and R are a memory aid we will use to remember the various forms of the equation relating voltage, current, and resistance. Around 1840, James Prescott Joule gave us Joule's first law, more commonly known in electronics as the power law. The power law relates power in terms of voltage and current. The unit of measure for power is the watt, which is named after the Scottish mathematician James Watt, who did extensive work on improving the steam engine. The volt, the amp, Ohm's law, and the power law are all foundational elements in the study for this course. Other notable advancements in electronics happen quickly. A selected list of achievements is as follows. Alexander Graham Bell invented the first practical telephone in 1876. Thomas Edison, one of the world's most prolific inventors, patented the phonograph in 1878. In 1880, he developed the first commercially practical electric light and also patented an electric distribution system. Heinrich Hertz in 1888 discovered radio waves. Vladimir Zworykin in 1924 developed the picture tube. Eckert Macaulay developed the first digital computer in 1946. Perhaps one of the most important developments for commercialization in electronics is the invention of the transistor. Shockley Bardeen Brattain of Bell Labs invented the transistor in 1947. Also of Bell Labs, Gerald Pearson invented the solar cell in 1954. Jack Kilby Robert Noyce of Fairchild Semiconductor invented the integrated circuit in 1958. And Ted Hoff of Intel fame invented the microprocessor in 1969. We have come a long way since Ben Franklin's famous kite experiment. We need to take a moment to say thank you to these brilliant people and others who have diligently worked to bring us an understanding of electricity. It is because of their work we can do many fun and interesting things. We stand on the shoulders of giants. There are some basic theoretical ideas in the study of electricity. Understanding them will help us with our projects, giving us knowledge to build strong, reliable circuits. In this section, we'll look at exactly what electricity is, and then take a look at some basic electric circuits. We'll examine the difference between AC and DC electricity, and study the behavior of electricity in a circuit by exploring the properties of voltage, current, and resistance. Then we'll wrap up the theory section with Ohm's law and the power law. What is electricity? Electricity is a mysterious entity. It is sometimes difficult to describe and understand exactly what it is. To try and understand, we need to get back to basics, back to the very element of matter that makes up all things, the atom. All matter is made of atoms. This is a diagram of a lithium atom. All atoms are made up of neutrons, protons, and electrons. Neutrons have a neutral electric charge, protons have a positive electric charge, and electrons have a negative electric charge. Normally, an atom has a neutral charge. It has the same amount of electrons and protons. Electrons, however, can be easily moved from or to the electron orbitals of an atom, either by losing or gaining electrons, thereby becoming either positively or negatively charged. Electronic circuits have electrons moving through them in a multitude of ways. The study of electronics concerns itself with directing these electrons to achieve the desired effect with electronic components. The electronics designer is the coach, the components are the playing field, and the electrons are the players. A definition of electricity states, electricity, a form of energy resulting from the existence of charged particles, such as electrons, either statically as an accumulation of charge or dynamically as a current. The definition further refers to two types of electricity, the first being static or static electricity, and the second dynamic or an electric current. Static electricity is exactly that. It is an electric charge that is not moving. A great example of this is rubbing a balloon on a sweater or your hair and sticking it to a wall. The charges sit on the surfaces of the object, yet don't move. An imbalance of electric charge causes the surfaces to attract or repel. Like charges repel, and opposite charges attract. Let's take a look. Here we see a wool sweater, a balloon, and a wall. We see the charges on each object by the red positive charges and the blue negative charges. To begin with, none of the objects have an imbalance of charge. All the surfaces have an equal amount of negative and positive charges. As we move the balloon on the sweater, we can rub off some of the electrons onto the balloons and have a net positive charge on the sweater and a net negative charge on the balloon. We can now see that the sweater and the balloon are oppositely charged, so they attract. As we move the balloon towards the wall, we see something interesting happening. The negative charge on the balloon repels the negative charges away from the location of the balloon. So where the balloon and the wall meet, we have a localized opposite charge, negative on the balloon and positive on the wall, which is why we can stick the balloon to the wall. Opposites attract. Electric current is what happens when electrons flow through a conductor, such as a copper wire. Electrons move from atom to atom, resulting in an electric current. We can see this here in a very simple circuit of a flashlight, consisting of a battery, a filament light bulb, some wire, and a switch. The animation gives a visualization of electron flow or current flow through an electric circuit. Any electric circuit, by definition, is any arrangement of electrical components connected so that there is some form of current flow. Typically, there is a current or voltage source and a number of components connected with wire or circuit traces or other conductive means. Circuits can range from very simple, like a flashlight, to very complex, like a computer. No matter how complex a circuit is, it can be broken down into a number of simpler circuits. All circuits can be analyzed as series or parallel circuits, or a combination of both. A basic series circuit consists of a source of electrical energy, like a battery or a solar cell, a load which does the work of the circuit, like a light bulb or a motor, some components and other devices, and of course some conductors to connect everything together. For a series circuit, everything is connected in series. In a series circuit, all the current flows through every device. A break anywhere in the circuit interrupts the flow of current. The circuit to the right is a series circuit. It consists of a battery as the voltage source, two light bulbs as the load, and a switch together with the connecting wires. All the current flows through each and every piece of the circuit. We see that if we open the switch, breaking the circuit, the current flow stops. Closing the switch, completing the circuit, current flow resumes. In parallel circuits, there are multiple paths for current to flow. Multiple components are connected in a ladder fashion. Current can flow through components without first having to flow through another component. Here we have a parallel circuit with multiple light bulbs. Breaking any of the rungs of the ladder doesn't affect the other rungs. To disable the entire circuit, we must first break the circuit at the power source. Completing the circuit at the source resumes current flow to the entire circuit. Many circuits are a combination of parallel and series circuits. Complex circuits have many paths for the current to follow. In this example, we see the current flows through a complex circuit. The animation gives you an idea of the different current through the different circuit elements. Many circuits are very complex. Analyzing them mathematically is complicated, and beyond the scope of this course. However, a large multitude of circuits are of simple complexity. Analysis reduces to identifying the series and parallel sections and combining the analysis on each section. Can you spot the series sections and the parallel sections in this circuit? We need to understand that all circuits, no matter how simple or complex, are made up of a combination of series and parallel circuits. Knowing this will help us design our circuits with confidence and skill, ensuring that they reliably do what was intended. All the circuits we have looked at so far are DC circuits. DC stands for direct current. It means that the current is flowing in one direction only. DC current is generated by DC sources, such as batteries or solar cells. The battery in your car or flashlight generates DC current. If current flows in two directions, alternating, we call it AC current, which is short for alternating current. Alternating current is generated by generators or inverters. Normally, our house current is of the AC variety. It alternates 60 or 50 cycles per second, depending where in the world we live. Here we have two identical circuits of a flashlight. Identical, except that the left circuit is powered by a DC battery, and the right circuit is powered by an AC source. We can see in the DC circuit current moving only in one direction. In the AC circuit, we see the current moving back and forth. In the DC circuit, from the voltage graph, we see that voltage is constant over time. In the AC circuit, we see that the voltage alternates in the form of a sine wave. This is characteristic of currents produced by generators in a power plant. In this course, we'll be dealing primarily with DC circuits, although we will take a look at some special cases of some special AC circuits. To get a feel for the properties of electricity and its behavior in a circuit, we need to understand in a general sense what the quantities of current, voltage, resistance, and power represent. We can use a water analogy, comparing electron flow through a conductor to water flow through a pipe to help us understand these properties. Current. Electrical current is the flow of electrons through a conductor, just like water flow through a pipe is. We can have small and large currents, depending on how much water flows through the pipe in a given time. Electrical current would be the amount of electrons flowing through a conductor in a given amount of time. Electrical current is measured in amperes, or amps for short. Voltage. Voltage is often referred to as the potential of an electric current. Using the water analogy, it is analogous to the pressure of the water in the pipe. The higher the voltage, the higher the pressure is. Pressure in a pipe depends on the source driving the flow, such as a pump. The same is true for pressure or potential in an electric circuit. The higher the voltage source, the greater the pressure or potential. Electrical potential is measured in volts. Resistance. Resistance is quite simply that, resistance to current flow. All materials resist the flow of electrical current to varying degrees depending on their properties. In the water analogy, this equates to restrictions in water flow in a pipe due to bends, fittings, valves, pipe friction, etc. Electrical resistance is measured in ohms. Power. Power is the amount of work being done in a circuit. It is the product of current and voltage. We have to think of work as a result of what is done and the energy consumed to produce that work. In the water analogy, we can think of how the flow and pressure act to turn a water turbine, for instance. In an electric circuit, this would equate to how the current and voltage work to drive an electric motor or a light bulb, for instance. Electrical power is measured in watts. Here we see our electrical circuit alongside our water analogy. The electrical circuit has a voltage source, some conductors, and a device for work, that is the light bulb. We can see the current flow represented by the electrons flowing through the conductors. In the water analogy, the power source is represented by the pump, the conductors by the pipes and tanks, and the object of work, the turbine. As we increase the voltage or pressure, we see that the current flow increases and also more work is done. That is, the bulb burns brighter. On the water analogy side, we see that the height of the water in the tank increases, representing the increase in pressure. The water flow increases in current, and the turbine spins faster, showing that more work is done. This simple water analogy gives a tangible illustration of how the electrical properties of current, voltage, resistance, and power relate to one another. Now that we know what current, voltage, and resistance are, we're ready to look at some math. Ohm's law is a simple equation that relates current, voltage, and resistance in terms of one another. The triangle with the V over the I and R is a memory aid to remember the different versions of the equations for Ohm's law. V represents voltage, which is sometimes designated with an E rather than a V. I is for current, and R is for ohms. The units for voltage, current, and resistance are volts, amps, and ohms. We can use Ohm's law to solve for one in terms of any of the others. So knowing any two of the three components, we can solve for the other. Current is the voltage divided by the resistance. I equals V over R. Voltage is the current times the resistance. V equals I times R. And resistance is voltage divided by the current. R equals V over I. Here we have a visual demonstration of Ohm's law. We can see the effects in the circuit by varying voltage and resistance with the sliders. Increasing voltage results in the current in the circuit increasing. Increasing resistance causes the current in the circuit to decrease. Decreasing voltage results in current decreasing. And decreasing resistance causes the current to increase. The mathematical relationship between power, current, and voltage is known as the power law. Power equals current times voltage, or P equals I times V. The unit of measure for power is the watt. This is an extremely useful equation, so remember it. We will use it a lot. Combining Ohm's law with the power law allows us to solve for power in terms of current and resistance. Here we see a chart showing all the possible equations relating current, voltage, resistance, and power. In the upper right quadrant, we see the equations for voltage in terms of current, resistance, and power. In the lower right quadrant, we see resistance defined in terms of current, voltage, and power. In the upper left quadrant, we see current defined in terms of voltage, resistance, and power. And finally, in the lower left quadrant, we see power defined in terms of current, voltage, and resistance. Keep this chart close by. It is a handy tool as we design our circuits. So this brings us to the end of our theory section. By now we should have a good understanding of what electricity actually is, and the difference between static electricity and electric current. We should be able to identify different types of electric circuits: series and parallel, simple and complex. We should also understand the differences between alternating and direct current and their sources. Through the water analogy, we should have a quantitative view of voltage, current, and resistance. The foundational equations of Ohm's law and the power law should now be a part of our knowledge base. These basic foundations have equipped us well as we now move to more practical applications in circuits. In this module, we'll take a look at starting to build some simple circuits using breadboards. Breadboards are handy little devices that let us quickly build circuits. Components are easily inserted into the breadboard and connections quickly made to work up live circuits. A breadboard circuit allows us to swap components and make changes to our circuits for experimentation. We can quickly see the practical effects our changes make and make adjustments to get the circuit performance we are looking for. For this section of the course, we're going to use a virtual breadboard called Fritzing. We'll use Fritzing as a teaching tool to show how we get from a schematic drawing of a circuit to an actual breadboard layout. You can download the latest version at www.fritzing.org. Fritzing allows us to create circuit sketches. Here we have opened an untitled sketch. With Fritzing, we can create the circuits in either schematic and render them into breadboard, or go straight to breadboard and the schematic is created automatically alongside. We'll start in breadboard mode. To the right, we see our parts menu. We can bring any number of parts into our workspace. Let's bring in a small breadboard. When a particular part is selected, we see in the lower right corner the part properties. We can select different configurations of breadboards by changing the properties. Here we can change the breadboard to a smaller version, a half version. And we can pick different configurations of breadboard just by selecting on the properties. We'll start with the half-size breadboard with our plus and minus buses highlighted. Breadboards come in various sizes, differing in the number of rows and columns they have. Most breadboards have similar configurations. You can use a single breadboard or multiple breadboards to build a circuit, each breadboard dealing with a particular aspect of a circuit. You'll soon get used to building circuits with breadboards and how they help to refine and streamline your designs. The spacing of the contact points is typically 0.1 inches or 2.54 millimeters. This allows for easy insertion of ICs of the same pin spacing. Other components can be inserted easily. With a few jumpers, complete circuits can be built up quickly. It is important to understand how the contact points are connected. The breadboard is separated down the middle with a channel. This is typically where an integrated circuit would straddle, so that all its pins land on isolated columns of contacts. The highlighted pins show areas of common electrical connection. The contacts are arranged in rows and columns. Each column, 1 to 30 for this breadboard, has contacts in rows A through E common and contacts in rows F through J common. Any device inserted into the same column in rows A, B, C, D, or E will be connected, and any device inserted into row F, G, H, I, or J will be connected if on the same column. The rows are not connected. Along the top and along the bottom, we have two buses. They are marked blue and red, or minus and plus, and are common through the whole bus. Anything inserted into the red or the plus bus will be connected, and anything inserted into the blue or the minus bus will be connected. These buses are handy to use as power supply rails or input and output signal rails. Before we can build a circuit, we need a schematic diagram. A schematic diagram, or schematic for short, shows us in symbol form the components and connections for our circuit. In the schematic editor, we can place components and connect them with wires. Let's build a really simple circuit, an LED flashlight. We'll select the components from the Parts menu. First, we'll need an LED. Next, we'll need some kind of power source. We'll use a battery. And most importantly, we'll need a current limiting resistor. The battery is capable of generating more current than our little LED can handle. We have chosen a super bright LED that will be happy with around 28 milliamps of current. Most LEDs are happy between 10 and 15 milliamps, but check the spec to be sure for your particular LED. Finding the symbol for the resistor, we place that into our workspace. We'll throw in a switch as well. Zooming in, and we'll just rearrange the components to make them a little bit easier to connect. Now we'll need to connect the components, so let's go to our parts list and look for the wire. Select our wire, and we'll make our connections. Now that we have our circuit all wired up, we need to select the properties of each component. We'd like to use a 9-volt battery, and the library defaults to a 3-volt battery, so we'll go to the properties for that. We'll select our 9-volt battery. Our switch is either through-hole, THT, or SMD, which is surface mount. We'll leave it at THD, which is through-hole. Our diode, we can leave it as 5mm through-hole, or, let's just for fun, put it 3mm through-hole. And the resistor is the one that we have to select in order to get the proper current flow characteristics through that diode. We had already mentioned we're going to use a super bright LED, which is quite functional at 20 milliamps. So using Ohm's law, the 9-volt battery, we need to calculate the value of the resistance. So calculating the value of R1, we use the familiar Ohm's law. And the version of the equation that we're going to use is R equals V over I. Now we know that the volts, V, equals 9, and that the current that we are looking for is 20 milliamps, or 0.02 amps. And substituting into the equation, we get R equals 9 divided by 0.02, which gives us a value for R1 of 450 ohms. We only have a 470 ohm resistor handy, so that's close enough. Going back to our schematic then, we'll select R1 as 470 ohms. And there we have it, our complete schematic circuit with proper values and component properties. Now switching back to breadboard mode, we can see how the software has placed our components in an actual real-world view. The little dashed lines show our circuit connections by what we would call air wires. They just show the circuit connection but aren't the actual connections yet. We're going to have to make those. So let's start moving our components around and actually wiring up our circuit. We'll move the switch. We can see the green highlighted areas that show the common buses for each portion of the connected terminal. We'll take the battery and we'll take advantage of the onboard circuit traces. So now we've made that connection. We'll take the resistor, put that there. We're almost connected. We're going to need a little wire. And that's our circuit. So all the air wires are connected, everything is connected up, and we have a fully functional circuit. So now there's only one thing left to do. We need to save this sketch. We're going to save it, and we are going to call it LED flashlight. There we go. We've saved that. Now that's about as simple as a circuit as we can get. A single series circuit with a switch, a resistor, a power source, and a load, which is our LED. Let's do something a little more exciting and build a circuit that flashes a light. For our light flasher circuit, we're going to use a standard 555 timer as the core of our circuit. The 555 timer is what we call a functional block in electronic terms. A functional block is a special circuit that has a number of discrete components on a single chip, resulting in a particular function. A strategic selection of a few off-chip components can give functional blocks very powerful uses. The 555 timer is an extremely useful little device, and it can operate in two modes. One is astable and the other is monostable. We're going to wire the 555 in a basic astable configuration and use the output to control the flashing of an LED. The parts that we're going to need for our 555 LED flasher circuit are as follows. We'll need a 555 timer, and since we're using a breadboard, we'll want the package variety of an 8-pin DIP, which stands for dual inline package. We'll need a 10 microfarad electrolytic capacitor, 16 volts or greater. We'll need a 1K ohm resistor, a 100K ohm resistor, and a 470 ohm resistor. All the resistors, their wattages aren't real important. We're not passing a lot of current through them, so your standard 1/8 or quarter watt resistor will be fine. We'll need a 9-volt battery and a battery strap. And of course, we'll need an LED. And we'll need our breadboard and jumpers. Now all our components should be through-hole components, which means they all have leads. We don't want any surface mount components or SMD components. Now I've already created a sketch in Fritzing for the 555 timer astable circuit. If you take a look at the schematic, there's a number of things that we can see here. Take for instance the battery. We can see that one end of it is connected to a 9-volt terminal and the other end to a funny looking symbol, which is actually the ground potential. We can see that everything that is connected in the circuit, although it's not physically connected on the drawing, that's marked 9 volts, is electrically connected, and also with all the ground connections. We have 2 9-volt connections and 3 ground connections. This is a way that we can clean up our schematics without having lines drawing all over the place. We just put symbols for common connections, and we assume that they are all connected electrically. Switching to the breadboard layout, we can see the components laid out, connected by air wires, ready to be placed on our breadboard. All that's left to do is put the components onto the breadboard and then make our connections with either the column traces on the breadboard or with jumpers. We'll do a combination of both. We'll do this in time-lapse photography here so that you can get a quick overview of how this is done. There are lots of ways to make the connections. You'll get the hang of keeping things simple and neat with some practice. For our basic astable circuit, the frequency of the oscillations is given by the equation 1.44 divided by R1 plus 2R2 times C1. We chose these values for our circuit so that the frequency of the flashing is about 1.4 cycles per second. Let's see what happens when we change the value of C1. Let's change it to a smaller value by a factor of 10. We'll substitute the 10 microfarad capacitor with a 1 microfarad capacitor. We should see that it flashes much quicker, 10 times quicker according to our equation. Going the other way, we'll put a 100 microfarad capacitor in place of C1. We should get a very slow oscillation, 10 times slower than the 10 microfarad value. Let's take a look. Here we have an actual circuit operating here with all the components as specified with the 10 microfarad capacitor. Let's try and change the 10 microfarad capacitor for the 1 microfarad. We see after swapping it that indeed the LED does flash a lot quicker. Let's try it with the 100 microfarad capacitor. We would expect a very slow flash rate. Trying again with the 1 microfarad capacitor. Quick flash rate. And back to our design capacitor of 10 microfarads. Roughly a flash rate of 1.4 cycles per second. For those who are interested, T1, or the on time, is given by the equation T1 is equal to 0.693 times R1 plus R2 times C1. And the off time, T2, is given by the equation T2 is equal to 0.693 times R2 times C1 for astable operation. We can see by manipulating the values of R1 and R2, we can adjust not only the frequency of the oscillator, but also the duty cycle. Try it out and see if you can think of some neat applications for this versatile circuit. Breadboards are extremely useful for prototyping temporary circuits and trying out different ideas. We'll be using this method primarily for this course to build our different demo circuits because it's easy and quick. Breadboards do, however, have their limitations. Very complicated circuits can get quite messy, and the jumpers can get knocked off if not careful. There is some contact resistance on the spring contacts, and this can make a difference in some circuits. High-frequency circuits are not well suited to be prototyped by breadboards, and surface mount components are right out. Breadboards are not a permanent or hardy circuit solution. Breadboards, on the other hand, can be used in conjunction with other methods to build some very complex circuits. Later on, we'll cover some more complicated and permanent circuit building techniques. It's time to start looking at some specific electronic components that are used to build circuits. We've already looked at a few components: the resistor, the capacitor, LEDs, and the 555 timer. Let's take a closer look at some of the basic building blocks of electronic circuits. You'll find that the vast majority of circuits are built with basic components, combined in different fashions to obtain the desired result. Very complex circuits can be broken down to these primary components. Components can be categorized into two basic categories. One is passive and the other is active. A passive component is a component that does not require energy to operate except for what is available in the circuit that it is connected to. The passive component is not capable of power gain and is not a source of energy. In the context of electronic technology, there are stricter guidelines for the term passive component. Electronic engineers view this term usually in correlation with circuit analysis, which involves methods of finding the currents through and the voltages across every component in the network.
We're going to use a very loose categorization of components, and in fact some of what we are going to consider as passive components could by definition be considered active components. Passive components that we are going to look at include wire and cable, switches, relays, resistors, capacitors, and once we've taken a look at these components, we'll look at a basic resistor-capacitor circuit. Wire is by far the most important common component in electrical circuits, so much so that it is taken for granted. It is very important, however, that the right type of wire be selected for each circuit and circuit element. Wire is a conductor, usually copper, and is usually covered by an insulator, most often plastic, rubber, or lacquer. It is either solid or stranded. Stranded wire is more expensive, so it is used in situations where the flexing of wire is likely to occur. A stranded wire has better flexing properties than solid wire. Your test leads for your digital voltmeter, for example, are made of stranded wire. The copper conductors are sometimes tinned, which makes it easier to solder. The current carrying capability of wire is determined by its diameter. Larger diameter wires can carry more current. The diameter of the wire is measured in gauge. Don't get confused here, as a larger gauge number means a smaller diameter. Small gauge is a larger diameter. Using a wire that cannot carry the current in a circuit will get you quickly into trouble. The wire will overheat and the consequences can be catastrophic. Always use conductors large enough to carry the current. A cable is simply a number of conductors bundled together or in a common jacket. Other considerations for wire selection, especially for signal wire, that is, wire carrying data, especially at high frequencies, is the capacitive quality of the wire. This is a function of the conductors and insulators used in the making of the wire or cable. Shielding from noise is also important, and a foil or braided shield is often found in signal wire. Coax, Ethernet cat cables, and audio cables all take these signal properties into consideration. The cables are designed and manufactured specific to the application. Here is a wire gauge that shows the relative sizes for standard wire gauges. Mechanical switches are used to interrupt or permit current flow in a circuit. They can also be used to direct current to different circuit paths, or to select different signals to be used in a circuit. There are countless configurations of switch circuits. They vary from single pole to multi-pole contacts. The action can be push button, toggle, slide, or rotary, and the contacts can be either normally closed or normally open. Let's take a look at a number of them to give you an idea of how versatile they are. Here is a schematic of a simple single-pole, single-throw switch. We call it single-pole because it only controls one circuit path. It is called single-throw because we can only select one contact point. We see the contact points on the switch drawn by the circles. The leads from the switch show the circuit connection points, and the switch portion in the middle shows how the contact is made between the two contact points. The short form designation for this switch is SPST, which stands for single pole, single throw. This switch is a single pole, double throw configuration. Still, one common connection, thus single pole. However, now we can select or direct to two different paths. The switch is always close to one of the circuit paths, either L1 or L2. The designation for this switch is SPDT for single pole double throw. Here's a symbol of a more complicated switch. Can you figure out the configuration? We would call this switch a double pole single throw. Double pole because we have two circuit paths we are controlling, and single throw because we can select only one contact per pole. Note the dashed line shows that the switches for each pole are mechanically connected. The switches therefore operate together. What would you say is the configuration of this switch? It is a double pole, double throw. Two circuit commons selecting two possible contacts per common. As you can see, we can build up switches, at least schematically, for any number of poles or contacts we need. Push-button switches are also quite useful. They control their contact closures by push action rather than toggle action. They can have the contacts momentary, that is, the switch needs to be actuated to hold or release the contacts, and a spring in the switch returns the switch to either a normally open or normally closed position when not actuated. The top switch is a single pole, single throw, normally open switch, and the bottom switch is a single pole, normally closed switch. Push-button switches can be momentary, that is, the switch action is only engaged when it is depressed, or it can be push on or push off, which toggles the switch closure with every actuation or pressing of the switch. Push-button switches can have multiple poles and contacts. Other switches include slide switches, rotary switches. Switches are even used as sensors when their actuator is connected to a sensing device such as a cam for positioning sensing or a diaphragm for a pressure switch. In selecting switches, always observe the switch's maximum voltage and current rating, and stay well below it to make sure the switch is not electrically overloaded. While technically not a passive component, electromechanical relays are worth mentioning here because they are a special kind of switch. They have poles and contacts just like the switches we have been looking at, but what is different is that the switches are actuated by a small electromagnetic coil. This allows a very small current needed by the coil to switch larger currents and voltages by means of the switch contacts. The relay is most often an interface device. We can use our small current electronic circuits to switch larger current real-world devices. Here are some schematic diagrams of some electromechanical relays. Note that the switch portions look exactly like our normal switch configurations, only the switches are actuated by the coil. When selecting relays, you will need to consider that the coil voltage is compatible with your electronic circuit, and also that the current and voltage rating of the contacts of the switches can handle the load you are switching. Next to wire, resistors are by far the most common component of electronic circuits. They all perform a crucial function, and that is to limit the current flow. We've already seen that the unit of measurement for resistance is the ohm. The greater the ohm value, the greater the resistor resists current, and inversely, the less conductive it is. Resistors come in many shapes and sizes. Other form factors are surface mount and through-hole configurations. You can find resistor arrays on a dual inline chip package or single inline packages. The type of construction of a resistor is important too. Resistance values can vary from very small resistances such as 1 ohm, and technically 0 ohms is not a resistance, but we can find resistors in 0 ohm packages. On the other end of the scale, we have resistors that measure in mega ohms or millions of ohms. The circuit and application determines the value we need. When resistors are manufactured, the value cannot be controlled precisely. Each resistor has what is called a tolerance. That is the value the resistor can vary by from its face value. Common tolerances are 10%, 5%, and 1%. For example, a 100 ohm resistor with 10% tolerance could range from 90 to 110 ohms in actual value. This is not usually critical in a circuit, but if it is, choose a tighter tolerance resistor. The same 100 ohm resistor with 1% tolerance would range from 99 to 101 ohms. One consequence of resisting current is that heat is generated. The heat generated can be expressed in watts, so a resistor that has a higher power running through it will be required to have a higher watt rating. Remember the power law? Higher power resistors are larger to dissipate heat, and some even have cooling fins. Choose a resistor that will handle the power it is dissipating. Most resistors are of a fixed value, but there are some resistors whose value changes, or have a variable value. There are adjustable resistors called potentiometers whose value can be changed by turning a dial. There are also variable resistors that change their resistance when exposed to light, pressure, or temperature. Resistors are identified by color bands. There are two color band systems, a 4-band code and a 5-band code. To see what the value of a particular resistor is, count the bands and use the color chart as we see here. For a 4-band coded resistor, the first two bands give the resistor's numerical value, which is multiplied by a multiplier in the third band. In this resistor, we can see that the first band is green, which corresponds to the value 5. The next band is blue, which corresponds to the value 6. And the third band is yellow, which multiplies the value from the first two bands by 10K, or 10,000. So we have 56 times 10,000, which is a 560,000 or 560K ohm resistor. The fourth band gives the tolerance, which for this resistor is a gold band, which corresponds to a tolerance of 5%. Similarly, for a 5-band code, the first three bands give the value of the resistor, the fourth band the multiplier, and the fifth band the tolerance. This 5-band resistor is red, orange, and purple for the first three bands, giving us a value of 2, 3, and 7, with the fourth black band giving us a multiplier of 1 ohm, resulting in a value of 237 ohms for this resistor. The final and fifth band is brown, giving us a tolerance of 1%. Resistors are shown in schematics in various ways. Some of the following are common schematic symbols. This symbol shows a fixed resistor. This symbol shows a variable resistor, or what we would also call a potentiometer. Note that it has 3 leads. The next symbol shows a photoresistor, or a resistor that changes its value with light. Can you guess what this symbol means? It represents a thermistor, which is a resistor that changes its value with temperature. Often resistors are connected in series like this. To calculate the total resistance of the resistors, you simply add the value of each resistor to calculate the total. For this example, we have 3 resistors valued at 220 ohms each. The total resistance, therefore, is 660 ohms. Finding the equivalent resistance for resistors connected in parallel is a little more complex. Here we have the same resistors connected in parallel. The equation for the total resistance is 1 over the sum of the inverse of the resistances added together. The equivalent resistance of this circuit is 73.33 ohms. Let's look at a very practical application of resistors. Voltage division is an often required problem to solve when designing circuits. We need to match outputs of one circuit to accept inputs from another portion of a circuit. Sometimes we need some voltage references, and resistors can provide the solution. The circuit we are going to analyze is called a voltage divider. We'll take a look at the circuit and then do a demo to illustrate its use. A voltage divider, in its simplest form, consists of 2 resistors connected in a series, one end connected to ground, and the other end connected to a voltage. We can see this in the following circuit diagram. As we can see, it is a very simple circuit, very inexpensive to build, just 2 resistors connected in series. The equation for calculating the output voltage in terms of the input voltage is Vout equals Vin times resistance A divided by the total resistance, which in our diagram is resistance A plus our resistance B. Let's solve a real-world problem, matching sensor input levels to A to D process levels. Let's assume we have a hardware platform that accepts 0 to 5 volt signals.
But the only sensor we could find to measure our physical quantity produces a 0 to 10 volt signal. We need a means of scaling the signal from 0 to 10 volts to 0 to 5 volts in order to be able to use the sensor. Here is our circuit diagram, again, except V in equals 0 to 10 volts and V out is equal to 0 to 5 volts. Looking at our equation again, V out equals V in times RA over the R total. Since our equation is ratiometric, mathematically it doesn't matter what the exact values of the resistors are, only the ratio of them. So for now, let's arbitrarily choose RA is equal to 1 k ohm. Then solving for RB, it is also equal to 1 k ohm. Let's do a mock-up of a real circuit. Here is our circuit diagram. And here is our actual circuit. We've built it up on a breadboard. Here we have resistor A connected to resistor B. And resistor A is connected to ground at this end. And the other end is connected to V out and one end of resistor B. And the free end of resistor B is connected to 10 volts, which is V in. Let's measure V in. That's 10 volts. And measure V out. And that's 5 volts, which is what we expected. So we've solved the problem with a resistor divider, getting a ratio of 10 volts to 5 volts. 10 volts V in, 5 volts V out. Sensor conditioning is another example of a voltage divider. There are many sensors that vary their resistance with respect to a physical property. Resistive sensors can be found that are sensitive to temperature, light, humidity, touch, location, pressure, vibration, as well as many other properties. The sensor conditioning circuit replaces one of the fixed resistors in a voltage divider circuit with a variable resistor. This converts the characteristic resistance of a sensor to a usable voltage. Let's take a look at temperature measurement, for example. We'll use a thermistor for the variable resistor. For a typical thermistor, the resistance versus temperature curve looks like this. This is the curve for a 10 k ohm resistor, which means the value is 10 k ohms at 25 degrees C. The curve is nonlinear, so in order to interpret this data, we would need to build a table or do some form of curve fitting in our process to relate the thermistor's changing value with temperature. But first, we have to get the changing resistance values into something our process can use, which is changing voltage values. Let's calculate the output voltage of our temperature sensing circuit for temperatures of 20 degrees C, 25 degrees C, and 30 degrees C. We'll assume that our process can accept a 0 to 5 volt signal, and we'll select RA equal to 10 k ohms. Using our equation, V out equals V in times RA over RA plus RB. The resistance versus temperature in tabular format for this range is as shown. So we find RB at 20 degrees C is equal to 12,260 ohms, RB at 25 degrees C is equal to 10,000 ohms, and RB at 30 degrees C is equal to 8,194 ohms. Substituting, V out equals 5 volts times 10,000 ohms divided by 10,000 ohms plus our thermistor. So for V at 20, it's 5 times 10,000 divided by 10,000 plus 12,260. And so on for V25 and also for V30. So solving, we get V at 20 degrees C, 2.246 volts, V at 25 degrees C equals 2.5 volts, and V at 30 degrees C equals 2.748 volts. Now this is something we can use in our process. We can measure it with our A to D inputs and linearize through code, tables, or equations, and then move on from there.
Let's look at a very practical application of resistors. Voltage division is an often required problem to solve when designing circuits. We need to match outputs of one circuit to accept inputs to another portion of a circuit. Sometimes we need some voltage references, and resistors can provide the solution. The circuit we are going to analyze is called the voltage divider. We will look at the circuit and then do a demo to illustrate its use.
A voltage divider, in its simplest form, consists of two resistors connected in a series, one end connected to ground, and the other end connected to a voltage. We can see this in the following circuit diagram. As we can see, it is a very simple circuit, very inexpensive to build, just two resistors connected in series. The equation for calculating the output voltage in terms of the input voltage is Vout equals Vin times resistance A divided by the total resistance, which in our diagram is resistance A plus our resistance B. Let's solve a real-world problem, matching sensor input levels to A to D process levels. Let's assume we have a hardware platform that accepts 0 to 5 volt signals. But the only sensor we could find to measure our physical quantity produces a 0 to 10 volt signal. We need a means of scaling the signal from 0 to 10 volts to 0 to 5 volts in order to be able to use the sensor. Here is our circuit diagram, again, except Vin equals 0 to 10 volts and Vout is equal to 0 to 5 volts. Looking at our equation again, Vout equals Vin times RA over the R total. Since our equation is ratiometric, mathematically it doesn't matter what the exact values of the resistors are, only the ratio of them. So for now, let's arbitrarily choose RA is equal to 1 k ohm. Then solving for RB, it is also equal to 1 k ohm. Let's do a mock-up of a real circuit. Here is our circuit diagram. And here is our actual circuit. We've built it up on a breadboard. Here we have resistor A connected to resistor B. And resistor A is connected to ground at this end. And the other end is connected to Vout and one end of resistor B. And the free end of resistor B is connected to 10 volts, which is Vin. Let's measure Vin. That's 10 volts. And measure Vout. And that's 5 volts, which is what we expected. So we've solved the problem with a resistor divider, getting a ratio of 10 volts to 5 volts. 10 volts Vin, 5 volts Vout. Sensor conditioning is another example of a voltage divider. There are many sensors that vary their resistance with respect to a physical property. Resistive sensors can be found that are sensitive to temperature, light, humidity, touch, location, pressure, vibration, as well as many other properties. The sensor conditioning circuit replaces one of the fixed resistors in a voltage divider circuit with a variable resistor. This converts the characteristic resistance of a sensor to a usable voltage. Let's take a look at temperature measurement, for example. We'll use a thermistor for the variable resistor. For a typical thermistor, the resistance versus temperature curve looks like this. This is the curve for a 10 k ohm resistor, which means the value is 10 k ohms at 25 degrees C. The curve is nonlinear, so in order to interpret this data, we would need to build a table or do some form of curve fitting in our process to relate the thermistor's changing value with temperature. But first, we have to get the changing resistance values into something our process can use, which is changing voltage values. Let's calculate the output voltage of our temperature sensing circuit for temperatures of 20 degrees C, 25 degrees C, and 30 degrees C. We'll assume that our process
Can accept a 0 to 5 volt signal.
and we'll select Ra equal to 10k ohms. Using our equation, V out equals Vn times Ra over Ra plus Rb. The resistance versus temperature in tabular format for this range is as shown. So we find Rb at 20 degrees C is equal to 12,260 ohms, Rb at 25 degrees C is equal to 10,000 ohms, and Rb at 30 degrees C is equal to 8,194 ohms. Substituting, V out equals 5 volts times 10,000 ohms divided by 10,000 ohms plus R thermistor. So for V at 20, it's 5 times 10,000 divided by 10,000 plus 12,260, and so on for V25 and also for V30.
So solving, we get V at 20 degrees C, 2.246 volts, V at 25 degrees C equals 2.5 volts, and V at 30 degrees C equals 2.748 volts.
Now this is something we can use in our process. We can measure it with our A to D inputs and linearize through code, tables, or equations, and then move on from there.
Capacitors come in many shapes and sizes and configurations, but they all do the same thing. They store an electrical charge. Let's take a quick look at a capacitor model. In this model, we see a capacitor made of two conducting plates separated by a dielectric. The plates are connected, one of them to the positive side of a battery and the other to a negative side of the battery. If we increase the voltage on the battery, we can see what happens to the charges on each of the plate. The positive side has a positive charge, and the negative side has a negative charge. Disconnecting the battery, we see that the charge remains. Changing the polarity from one side to the other, we see here the negative charge is now on this plate and the positive charge is on that plate. And the capacitor stores the charge that is placed on it by the battery. The capacitance of the capacitor is determined by a number of things. One is the plate area, the other is the separation between the plates, and the other is the dielectric in between the two plates. We can vary the capacitance by changing the separation in the plate area or the dielectric. Let's increase the separation and see what happens. Capacitance goes down with increased separation. Let's increase the plate area and see what happens. Capacitance goes up with larger plate area. And changing the dielectric also changes the capacitance. The measurement of capacitance is the farad. Just like resistors, capacitors can have very small capacitance values and go to very big ones. A 1 farad capacitor would be very big, and capacitors are usually orders of magnitude smaller in electronic circuits. Capacitors are often classified by what their dielectric is. Common materials are ceramic, mylar, paper, or even air. The dielectric is selected by the application of the electronic circuit. Different dielectrics have different costs. A ceramic capacitor is quite inexpensive when compared to a mylar capacitor. In digital circuits, the ceramic capacitor may be adequate, but in audio circuits, we would opt for the more expensive mylar capacitor because of noise concerns. In a power supply circuit, we may choose a tantalum or an electrolytic can capacitor because these capacitors can be made in large capacitance values required for power supply circuits. Proper selection of capacitors is an art in of itself. A circuit may work okay with one type of capacitor, but it may work great with another type, even so the value is the same. Just as resistors have to be selected with adequate power ratings for the application, so must a capacitor be selected with adequate voltage rating. You need to be aware of the maximum voltage that the capacitor may see in the circuit and select a capacitor that is rated above this voltage. and with an ample safety factor. Selecting a capacitor with too low a voltage rating will destroy it, and sometimes with great fanfare, which can be dangerous. Capacitors can have fixed or variable values. We can find variable capacitors such as trim capacitors that can be adjusted with a screwdriver. Older vacuum tube radios have large tuning capacitors with air as the dielectric. These were tuned to tune the frequency of the receiver. And some transducers will change capacitance proportional to the measured element. Many pressure transducers and touchscreens are capacitive devices. Condenser microphones are essentially a capacitor. Condenser is another word for capacitor. We already know that the unit of measurement for capacitance is the farad, but most capacitors are an order of magnitude smaller than a farad. A microfarad is 1/1,000,000th of a farad. It has the prefix of the Greek letter mu. A picofarad is 1/1,000,000th of a farad. It has the prefix of the lowercase p. There are many symbols to show a capacitor in a schematic. Some of the more common ones are fixed, nonpolar, fixed, polar. This means that you must install this capacitor with the plus sign to the positive side of the circuit, and variable or adjustable. The equations for total capacitance are somewhat different for capacitors than for resistors. For a series circuit, we just can't simply add the capacitances. The total capacitance is calculated by taking the inverse of the sum of the inverses of the capacitors in series. For this circuit, we have 3 capacitors of 2.2 microfarads each. Calculating, we have a total capacitance of 0.733 microfarads. Capacitors in parallel are, however, simply added up to get their total capacitance. The total capacitance of this circuit is 6.6 microfarads. Let's build a simple resistor capacitor circuit and illustrate how a capacitor charges and discharges.
In this circuit diagram, we have a capacitor hooked up in a couple of different ways. One is a charging circuit and one is a discharging circuit. For the charging circuit, which is the lower loop, we have the capacitor hooked up to a 10 ohm resistor, through a switch, through a 9-volt battery, and then with a return leg back to the other side of the capacitor. The discharging circuit, which is the upper loop, eliminates the battery and is connected to a 10 ohm resistor and a switch, and that to the other side of the capacitor. If we close the switch on the lower loop, on the bottom loop, the charging loop, we'll be able to see on the voltmeter how the capacitor charges. Let's give that a try. We see the voltage rising to the final value, which would be the same as the 9-volt battery. If we remove the battery from the circuit, we see as before, the capacitor holds the charge, remains at 9 volts. If we close the other switch, we'll be able to discharge the capacitor. Same value resistor, no battery, but we're discharging through the 10 ohm resistor. And we see a very typical discharge curve and back down to 0 volts. The RC time constant in RC circuits is very important. It is the time in seconds that it takes for a capacitor to charge to 63.3% of its final charge. This is a 9-volt battery, so 63.3% of 9 volts is approximately 5 volts. Let's count and see how long it takes to charge to 5 volts. 1,000, 2,000, 3,000. About 3 seconds. If we look at the discharge curve, since our values are the same, we should see the same time. Coming down from 9 to 4 volts is going to be our RC time constant. Let's try that. 1,000, 2,000, 3,000. So this circuit has an RC time constant of approximately 3 seconds. Let's take a look at that one more time. Charge. Open the switch and discharge. The application for RC circuits is commonly used in filters such as frequency high pass or frequency low pass, band pass filters, and such. We also see them in DC power supplies and audio circuits. Let's take a look one more time. Here we see charging and discharging.
There are basically two types of electronic components, passive and active. Passive components do not require energy from the circuit to work. We looked at typical passive components such as wire, switches, relays, resistors, and capacitors, and how they can be combined. While basic, resistors and capacitors can be arranged to give some very useful circuits, such as voltage dividers and RC circuits, which are building blocks for other special circuits. They are the bread and butter of our electronic circuits. Most circuits are a combination of passive and active components. Active circuits need both passive and active components alike. Active components are the exciting components in an electrical circuit. They do some pretty exciting things. Electronics get real interesting real fast when we start to use these mysterious devices. We've laid the background on electrical theory and applied it to passive components. All the theory still applies to the active side of things. This section is designed to give you an overview of active components and devices. The subject is so broad and vast, yet knowing what we are about to cover will give you a sound basis for future application and study. In our previous module, we looked at passive components. That is, components that do not require power or energy from an external source to perform their operation. All the energy they need to perform their function comes from the circuit they are installed in. Active components, on the other hand, need an external power source or supply to perform their function. This is specifically what separates active from passive components. Active components need an external power supply. For the most part, active components are made with silicon. Active components made with silicon are called semiconductors. There are two types of silicon used in the manufacturing of semiconductors. One we call P-type, and the other we call N-type. P-type silicon has a shortage of electrons in its molecular structure. N-type silicon has an excess of electrons in its molecular structure. Devices are built by layering these two types of silicon in silicon sandwiches. The way this is done gives our semiconductor devices certain properties. We cover a number of devices so you can get an understanding of what they do and how they work. We will focus our study on 6 different active components and how they function. We'll take a look at the diode, the transistor, the SCR or silicon controlled rectifier, the triac, integrated circuits, and application-specific circuits, which are special cases of integrated circuits. Our diode is the simplest of semiconductor devices. It is made up of only 2 layers, one of a P-type silicon and the other of an N-type silicon. Diodes are usually encased in plastic or glass cylinders with lead wires attached to the P and N layers, but sometimes you can also find them encased in metal cans or with big heat sinks for high power applications. Other form factors can be found as well. Diodes essentially operate as one-way valves. They only allow current to flow in one direction and block it in the other direction. This is the schematic of a diode. The leads are designated as the anode and the cathode. The anode is designated by an A, always at the triangle end, and the cathode is designated by a K. You can think of the triangles as arrows, which on schematics show the opposite direction of current flow. The reason the arrows appear the wrong way, so to speak, is that early in the history of electricity it was assumed positive charges flowed, not negative. The symbols indicated positive flow, when we now understand it to be negative flow. The symbols remained, so we just need to remember to think inversely when looking at schematic symbols. Current flows through a diode when the anode is more positive than the cathode. In fact, the anode needs to be about 0.6 volts greater than the cathode in order for the diode to conduct. Diodes are primarily used in rectification. That is, they are used to change or rectify an AC voltage into a DC voltage. There are two types of rectifier circuits. The first type is what is called a half-wave rectifier. It is called that because it only allows the positive values of an AC wave to pass. The negative portion is rejected or blocked, and the resultant output is half of the original wave. So moving from left to right in this diagram, we see the original AC signal. As it passes through the rectifier, which in this case is a single diode, and yields the modified waveform. This is a raw half-wave signal which can be further filtered and smoothed using RC circuits. The second type of rectifier is a full-wave rectifier, or more commonly called a bridge rectifier. This rectifier consists of a bridge configuration of 4 diodes. 2 nodes of the diode bridge are connected to the AC waveform, and the other 2 nodes output the full-wave rectified signal. There are many kinds of diodes available with many package variations. In this picture, we see some surface mount diodes, some through-hole diodes, some glass-encased signal diodes, and we also have several packages that have 4 diodes installed in a bridge configuration to give us convenient packages for bridge rectifiers. As with all components, we must respect the physical limitations of the devices we are using. We need to know what the voltage and current requirements will be for the circuit that uses the diode, so we can select a diode that will withstand the maximum voltage and current ratings. It's a good idea to select an ample safety factor. Always observe and respect the maximum voltage and current ratings. Diodes need a minimum voltage to conduct in the forward direction. Typically, this is 0.6 volts. You need at least this voltage for the diode to conduct. LEDs are a special case of diodes. Their purpose is not to rectify, but to give off light when a current passes through them. Therefore, they are usually designed for very small currents. You need to always use a current limiting resistor when using an LED to prevent it from burning out. The current blocking properties of diodes make them extremely versatile and useful, especially in power supply circuits and also protection circuits, where they are commonly found. Take a look at any circuit board and see if you can find them. Transistors are semiconductors with 3 layers. They are laid up in alternating P and N silicon in either a PNP or an NPN arrangement. Here are the schematic symbols. You can remember which is which by remembering that NPN can also stand for not pointing in on the arrow of the NPN transistor. Transistors allow a small current to control a larger current. A small fixed or varying current on the gate of the transistor can make it behave as an amplifier or switch. The leads of the transistor are identified as the base, the collector, and the emitter, or EBC. The emitter is always the one with the arrow either pointing in or out. The base always connects to the middle layer of the 3-layer sandwich of the transistor, and the collector is the remaining lead. A very small current at the base of the transistor will allow a much larger current to flow through the emitter-collector path. There are many types of transistors. What is common to all transistors is that they all have 3 leads and perform the same function. controlling larger currents with smaller ones. The properties and application can be somewhat different between each type. Different types of transistors include field effect transistors, or FETs, metal oxide semiconductor FETs, or MOSFETs for short, JFETs, and unijunction transistors, to name a few. We're going to focus our study on the very humble bipolar transistor. In looking at the transistor as a switch, the base functions as a gate. If the base is at 0 volts, common with the emitter collector path blocks any current flow. If the base is at a value greater than 0.6 volts, which is the minimum forward voltage, and common with the collector, the emitter collector path conducts. We see this in the following examples. If we ground the base through R1, the emitter collector will not conduct. That is to say, the gate is closed, and the LED will not light. R2 is there to limit the current flow to the LED when the switch is on, as we shall see in our next example. In this example, the base is raised to the positive voltage rail through R1. Now the gate is open, and the emitter collector path will conduct, causing current to flow and light the LED. R2 is chosen to limit the current to around 10 milliamps for this LED. We just can't get away from Ohm's law. I know what you're thinking. No, this is not me playing my favorite pop tune, but it does show us an example of a practical application of an amplifier. The guitar amp is a very complex amplifier, composed of many stages of amplification and other circuitry. The initial stage would be to amplify the very small signal from the guitar pickup to levels that the later power amplification stages can use. We can use the same concept to get signals from sensors such as temperature and light sensors to a level that is useful in our signal processing circuits, such as the analog to digital converter in our microprocessor. With a single transistor, we can achieve gains from millivolt levels to voltage levels typically required for processing and measurement. Let's look at a simple transistor amplifier. Here we have a schematic of a simple transistor amplifier. Moving from left to right on the diagram, we start with the small waveform signal. We use an input capacitor, also called in this instance a decoupling capacitor. Its purpose is to remove any DC from the signal we are interested in and only pass the AC signal, coupling it to the base of our transistor. In this simple transistor amplifier, the base acts more like a valve, like the valve on your faucet at home. The more current to the transistor base, the more open it is. The less, the more closed. Similarly for a water faucet, a small turn of the faucet valve can control a large flow at the spout. The bias resistor pulls up the input to the base so the entire signal is above the 0.6 volt minimum forward voltage of the silicon junction. This ensures that the entire waveform will be amplified and prevents distortion at the output. Our load is required to change the current through the emitter collector path to a voltage. Remember Ohm's law again? The resultant output is one that is an amplified version of the input. Selection of specific component values will depend on the application. We've already seen that there are many different types of transistors. They can also be categorized according to application. The transistors at the top are small signal or switching transistors. The ones at the bottom are power or high current transistors equipped with mounting flanges to mount to heat sinks. Always respect the current and voltage limitations of transistors and be sure not to connect them the wrong way. Once the smoke is out, it's hard to get it back in. The SCR, like the transistor, is a 3-lead semiconductor device. It is a thyristor. It is like the PNP transistor with an additional N layer. Here we have the schematic symbol. The SCR switches DC current and can only be full on or full off. Unlike a transistor, it cannot amplify. The 3 terminals are called the anode, the cathode, and the gate. A small gate current on the SCR will cause it to conduct, Once the SCR conducts, removing the gate current does nothing. The SCR switching action is latching. In order to interrupt the current from the circuit, power must be removed in order for the current to stop. Here we have an SCR in a circuit to switch a DC motor. S2 is normally closed, S1 is normally open. Closing S1 places a small gate current on the gate of the SCR. Current then flows in the motor circuit. In order to turn the motor off, we must first interrupt the motor circuit by opening S2. In this circuit, S1 starts the motor and S2 stops it. The TRIAC is also a thyristor, and it is a 5-layer device. Here's the schematic symbol. It switches AC current. Like the SCR, it is either full on or full off. Unlike the SCR, it is not latching. The terminals are gate, main terminal 1, and main terminal 2. MT1 and MT2 for short. Placing a small current on the gate will cause the TRIAC to conduct. Removing the current stops the current flow through the TRIAC. Here we have a TRIAC in a circuit to switch on an AC motor. Closing S1 places a small gate current on the gate of the TRIAC, causing the TRIAC to conduct. Current then flows in the motor circuit. In order to turn the motor off, we simply open switch 1, which removes the current from the gate of the TRIAC, interrupting the current in the motor circuit. We've taken a look at the basic discrete components, the diode, the transistor, the SCR, and the TRIAC. Integrated circuits combine any number of these onto a silicon chip. Thousands of devices can be combined and connected on a chip to perform a particular circuit function. Even so, there are so many devices on a chip, it is still very small, and therefore is usually encased in a plastic package with leads to facilitate dropping these IC circuits into the designer's project. Integrated circuits can be categorized into 3 basic types of categories. The first is digital. Digital ICs take the digital input signals and process them digitally. The output, then, is also digital. The inputs and outputs of a digital IC can be of only one of 2 states, on or off, or high or low. We can also refer to digital ICs as logic. The next category is analog. Analog ICs accept modulating signals and process them accordingly. The output signal is a mathematical function of the input signal. Analog ICs are also therefore referred to as linear. The third type of IC is the application-specific IC, or functional block. Functional blocks will combine any number of analog or digital functions to produce a very special and specific function. An example of this would be an analog-to-digital converter, which is a chip that accepts an analog signal and converts it to a binary signal for digital processing. Logic ICs are a collection of gates. Gates are circuits that take binary inputs and output a logical decision based on the type of gate. Different types of gates are AND and NAND, gates shown by the symbols on the left. Also, OR and NOR, and exclusive OR and exclusive NOR, 6 basic types. The gates shown have 2 inputs and 1 output. Gates can have more than 2 inputs. Gates can have multiple inputs for greater decision-making power, and some special gates can have only 1 input, such as an inverter, which gives the inverse of the input, a NOT gate. Truth tables show us the particular output of a gate based on the state of its inputs. For the AND gate, we see that the output is only high when both the A and B inputs are high. The NAND gate, on the other hand, has exactly the opposite. The output is high except for the instance that inputs A and B are high. Similarly, the truth tables for the OR and NOR gates, The output of the OR gate is high when either the A or B input is high. For the NOR, the inverse is true. The output is low when either the A or B is high. For the XOR and the XNOR gates, the truth tables tell us that the output of the XOR gate is high when either the A or B input is high, but not both. For the XNOR, the inverse is true. The output is low when either the A or B is high, but not both. Gates are usually combined in logic packages. Here we see 4 AND gates packaged into one IC package. Note that we have 2 additional connections besides the gate connections. We have the power supply ground on pin 7 and the power supply positive, or VCC, on pin 14. This is a very common arrangement with logic families, 14-pin packages with power supplies on pins 7 and 14. There are many families of logic available based on current technology. The main families you will come across are TTL and CMOS and a variation of them. TTL, which stands for transistor-transistor logic. TTL has in the past been the most popular and largest family of logic ICs. Other types of logic families are now available and are growing in popularity. TTL needs 5 volts to operate. In comparison to modern logic families, they use a lot of power. Today, they are not generally found in use where power concerns are an issue, such as battery-powered applications. Where TTL does excel is in its speed and robustness. Where speed of processing is important and a robust circuit is needed, then TTL is the choice to make. The main designation for TTL is the 7400 series. The quad 2-input AND gate to the left would be a 7408 package in TTL. CMOS stands for complementary MOS and is growing in popularity. CMOS once had the disadvantage of being slower than TTL, but now we have high-speed CMOS which rivals TTL for speed. CMOS also consumes much less power than TTL and can operate on a wider spectrum of supply voltages, typically 3 to 15 volts. CMOS does have one drawback, in that it is vulnerable to being damaged by electrostatic discharge. Circuits using CMOS need to take this into account. Good ESD practices when handling chips is necessary. The main family name for CMOS is the 4000 series. The quad 2-input AND gate to the left is a 4081 package in CMOS. The spectrum of linear circuits is vast. What defines a circuit as linear is that the output of a linear circuit is a functional relationship of the input. A versatile linear IC is the operational amplifier, or op-amp for short. The schematic diagram of an op-amp is shown here. We see that there are 2 inputs and 1 output. The input with the negative sign is called the inverting input, and the input with the positive sign is called the non-inverting input. We have connections for a power supply, both negative and positive. The maximum voltages that an op-amp can produce at the output are limited by the voltages Vs minus and Vs plus. This is what is called the rail voltages, and most op-amps can generate outputs from rail to rail. Just by choosing a few external components, the op-amp can be connected to perform many functions. The op-amp is often called an analog computer, as it can perform addition, multiplication, integration, and differentiation math functions. It can also compare inputs. Since there are many applications to consider, we'll just look at the op-amp as an amplifier, which is the same as the multiplication function. Here we have an op-amp configured as a non-inverting amplifier. The input is connected to the non-inverting input. R2 is a feedback resistor from the output connected to the inverting input. And R1 together with R2 give us the gain of the amplifier. The gain for this non-inverting op-amp is 1 plus R2 over R1. The voltage output therefore in terms of gain and voltage input is V out is equal to 1 plus R2 over R1 times V in. There are thousands of chips that are designed to perform a specific application. If you have a need for a particular circuit, do a search first to see if there's a chip that is available that already performs the function you are looking for, or something that is close. Chances are it already exists and can save you a ton of work. Implementing them into your design may be just a simple task of selecting a few external components to serve your application. Typical applications are communications drivers, motor control, sensor interfaces, power supplies, and a myriad of other applications. The 7800 series of linear voltage regulators are just one of those flagship components you will find in countless circuits. The 7800 series are 3-terminal positive voltage regulators. The 3 terminals are input, output, and ground. The prefix 78, followed by the voltage of the chip, determines its output. This particular chip is a 7805 for a 5 VDC output. Design is simple, with just a few selection of external components. Power supplies are quickly and easily designed, allowing you to focus on other aspects of the circuit. This is a typical application for 7800 positive voltage regulator. We start with an AC source. The step-down transformer drops the AC voltage to an acceptable level for the input of the 7800 regulator. Next, the AC signal passes through a full-wave rectifier bridge and then is immediately filtered by the filter capacitor. This then presents a DC input, yet unregulated signal to the input of the 7800 voltage regulator. The 7800 takes this signal and provides a regulated signal at the output. External component selection is specific to the application. Always select components to meet the voltage and current requirements expected in the circuit. And never, never, never work on live AC line current. And close and insulate all exposed AC connections and disconnect power when working on an AC line circuit. Active components, unlike passive components, need a power source to perform their function. They are semiconductor devices made from multiple layers of P and N silicon. Integrated circuits can employ many hundreds and sometimes thousands of discrete devices on a single piece of silicon. Active components can be found in digital, analog, and application-specific packages. The spectrum is vast, and we have only looked at a few. The best way to learn more is to try and build something. Our next module shows us how to get started in circuit construction techniques. When we are working in electronics, we more than likely are trying to build something useful. When all our study and design is done, we'll have to pick a way to physically work out the circuit. We're going to take a look at 3 different methods: the breadboard, perforated board, and printed circuit boards. Breadboards are essential in our experimentation with circuits. They very quickly allow us to change things and see what effects those changes make. One drawback for breadboards from a circuit perspective is that they are at best temporary. Not many applications will allow a breadboard as a permanent circuit. They are generally only suitable for through-hole components. Surface mount components are nearly impossible to implement into a breadboard without special fixtures. Complicated circuits are more difficult with breadboards. Breadboards excel for simple and quick experimentation. Complexity can be increased using a combination of methods such as circuit board shields and header strips. Perf boards are a step up from breadboards. They allow us to insert components through holes, usually spaced 0.1 inches apart. The leads can then be bent over on the other side and connections made by soldering leads and jumpers together. Some perf boards have copper traces on them that you can use as a pseudo-printed circuit board. Perf boards are better suited to through-hole components, but there are some specialty perf boards that have surface mount footprints on them for surface mount components, as well as holes for through-hole components. Perf board circuits are more permanent circuits, but they are time-consuming to construct. They are better adapted where one-off or very simple low-volume circuits are required. Here we see a sampling of various perf board circuits. The circuit on the lower right shows how the connections are made. Components and connections can be made on either side of the board. Anyone working in electronics will sooner or later want to start making circuits with printed circuit boards. Advantages to building circuits on a printed circuit board are that all types of components can be used with equal ease. Through-hole, surface mount, and fine-pitch components are easily implemented. PC boards are most suitable for commercial production. Assembly of the components on the board is done with special robots, making the cost per board very affordable at volume. You can render a complex circuit on a PCB as easily as a simple circuit, using PCB software readily available to the individual designer. While it is possible to make a simple PCB without software, not many people do this anymore with the advent of accessible PCB software. There was a time the only way to make a prototype PCB for the experimenter was to take a board with a full copper plane on it and apply resist to the circuit traces. The whole board was then dipped in a very strong chemical that would etch the remaining copper away, leaving the required traces. Holes then would be drilled, and then finally you had a crude board. Commercial quality boards were out of reach for the average individual without incurring a very large first cost. Thankfully, we live in a more modern age, and it is fairly easy now to generate a high-quality circuit board using PCB software and the services of a board house for a very reasonable price. PCB software packages have a number of common features. Being able to lay out a schematic is very handy. Some of the schematic examples in this course have been done with a PCB software package using the schematic feature. The neat thing about entering the schematic is that the software package begins to build the board layout in the background as you build the schematic. Parts in the layout portion can then be repositioned and the board sized to meet physical requirements. Next we have routing. In the layout, the components are connected with air wires. No real traces yet. The routing function of the software allows you to render these air wires into actual circuit traces. Some PCB software packages can do this automatically for you, based on a set of rules you define. Most boards are routed using a combination of auto-routing and manual routing methods. Board houses require specific data in the proper format to manufacture a circuit board. This data is input into their PCB making machinery. PCB software programs will allow you to generate the manufacturing files that you can send to your board house. Fritzing is an interesting piece of software freely available on fritzing.org. It is open source, available as a free download. It has the interesting feature that can simulate your circuit on a breadboard on screen, so you can use this as a template and render it physically. It allows you to make schematics and also lay out your circuit board. It is highly geared to the Arduino community and has a number of suppliers that can supply pre-assembled experimentation kits that can be used to experiment with their preloaded circuits. There is an active online community. Some disadvantages are that it has limited parts list. It is really for very simple projects only. It lacks many higher end features such as error checking, multiple layers, etc. It is, however, under constant development, and contributors from the open source community will no doubt continue to improve and add features to Fritzing as time goes on. It is overall a great package to get started with in electronics. It's worth the time to get familiar with it. This is what the environment of Fritzing looks like. When we open it up, it shows us a blank sketch. Circuit boards in Fritzing are called sketches. Let's load up one of the preloaded sketches. This is a sketch of a simple 5-volt regulator from the 7800 series. Fritzing has this neat little window where we can see it all assembled on a breadboard. We can move the parts around, place them, select new parts, and build our breadboard here. In the schematic view, we can see how the components are connected. In the PCB view, we can actually see how things are connected. We can take components and move them around, replace them, can move traces, and just design our layout right in this view. So breadboard, schematic, PCB. Eagle is a professional PCB circuit board program that has a light version available for free download for non-commercial use. The light version has all the features of the full professional version and is only limited by board size, 100 by 80 millimeters, and a maximum of 2 copper layers, top and bottom. All features such as component libraries, schematic, layout, routing, and CAM features that are found in the professional version are included in the light version. The parts library is immense, and custom part creation is fairly easy. Very complex boards can be made. The licensed versions can make multi-layer boards of any size. There are few cons with Eagle. It is a well thought out professional package. The limitations of the light version are not much of a restriction for the entry-level user. It may take a little more effort to learn Eagle, but for the serious designer, that little bit of effort is worth it. This is the control panel in Eagle. Projects in Eagle are called projects. Let's take a look at a sample project. We'll go to the Hexapod folder. The project opens up into the schematic of the Hexapod project. As we can see, this is a more complicated project than our previous one. We can open the project in board view, which shows us how the circuit is laid out in the actual circuit board form. We can see all the components connected with circuit traces. The red traces are the bottom and the blue traces are the top. This is a two-sided board. We can turn layers on and off. Now we see only the bottom layers. And now we see only the top layers. We can turn all layers off, and then we see only the components. The green circles are the pads where the leads will go through. We can toggle from the layout screen to the schematic screen just with one button. We click on this button to generate the manufacturing data for a board, and we run the project with the rules that we place into the project. So as you can see, Eagle is a little more complex, but it is much more comprehensive. The Hexapod project fits into the dimensions of the light version of Eagle, which is available for free download for non-commercial use. So as you can see, we can do fairly complex things with Eagle, and it's a great piece of software for those serious about making professional quality circuit boards. There are lots of ways to assemble a circuit, by hacking it together with low-tech perf boards to fully automated assembly of printed circuit boards. Circuit design and assembly is a process. Sometimes it is more like an art than a science. Circuit refinements will surely become necessary as the process moves on to improve performance, reduce cost, and add features. Sometimes a hand-built unit is sufficient for a single-purpose design. The more sophisticated a circuit is, the likelihood that more technological construction techniques will be required. If the goal is mass production, the PCB design is likely going to be the method as unit costs come down at higher volumes. So we've come a long way, and we have touched on many things in our introduction to electronics. We've taken a look at the history of electronics, the early discoveries and advances, and the people instrumental in the development of electricity and electronics. We've covered some basic theory and formulas to get you started in designing your own circuits. If you learned only one thing from this section, Ohm's law would be it, as it will get you a lot of mileage in electronics. We did a tutorial using a breadboard to help you get started in building experimental circuits. Breadboards are instrumental in building your knowledge through trial and experimentation. We studied the basic passive components, such as the resistor and the capacitor, and took a look at the math for combining components in series and parallel connections. We were introduced to semiconductor devices and looked at the discrete components, such as diodes, transistors, SCRs, and triacs. We also looked at how digital ICs and linear ICs worked and touched on some applications for application-specific ICs. And in our last module, we took a look at how we might construct our circuits. We looked at basic methods to sophisticated methods, from through-hole to printed circuit board. It seems like we're just getting started, and in a very real sense we are. What are the next steps to increase your skill and knowledge in electronics? Going further. Data sheets and data books from chip suppliers are valuable sources of information. Chip suppliers usually give examples of circuits with their data sheet to give suggestions on typical circuits. I have an old linear book from National Semiconductor that I got over 20 years ago and still use it as a valuable reference. Much of this data can now be found online by doing a simple search, although for old school people like me, I like having the volumes in my library. Component suppliers are a treasure trove of information for electronics knowledge. Most suppliers do the majority of their business through their web stores. There are too many to specifically mention. Browse their stores and you will learn a lot. If you live in a major center, there is likely an electronics club, such as a hacker or makerspace or lab. Members can share the resources there, tools, measuring instruments, and other cool stuff, and learn from others interested in electronics. Many have courses and bring in speakers to talk on particular aspects of electronics. No hackerspace in your area? Maybe you could start one. The online community is loaded with forums and chat spaces on many different subsets of electronics. There are people interested in audio, Arduino, automotive, automation, just to name a few. Blogs and even online electronics TV shows exist that can give you beneficial information in the area of electronics you are interested in. Many suppliers have pre-assembled kits for different interests. These kits are usually educationally focused, and you can learn a lot about the technologies involved as you build them. It is a quick way to build confidence and interest in electronics, and it's always satisfying to build something that has been pre-tested and works right away. I like this last slide. It says do it, which is a subset of don't quit. In electronics, you never arrive. There is a limitless source of knowledge to gain, but you have to start, so go build something.